Fanghua Lin, Professor Fanghua Lin from NYU that everybody probably knows. And so today he will talk about critical point sets in elliptic homogenization.
Okay, thank you very much for inviting me to this seminar series. It's a great pleasure to give a talk here. So I'm going to talk about recent work. We just posted a preprint on arXiv a few weeks ago. So that is dealing with critical point sets in elliptic homogenization. You can say, what's the motivation for that? Well, not really great motivations, but it's a natural question because people have been involved to study nodal set and critical point set, say for harmonic function or for solutions of nice elliptic PDE. So it's very natural to consider this problem. But on the other hand, it's from very beginning, you see right away, so that practically every tool used in dealing with nodal set, say of a harmonic function or smooth PD, does not seem to apply when you have a highly oscillating coefficient. Okay, so even from technical point of view, it's become interesting. But it's one.
Just to clarify, what is critical point set? Maybe it's
critical point set is like a solution U, which is not constant, and you look at the zero set of a gradient. I will define.
Oh, I see. Okay.
Okay. So let me look at the setup. So this is joint work with Zhongwei Shen. Okay. So the setup. So we have L epsilon U epsilon equals 0 in 2D, in ND, say both B2, and epsilon is supposed to be extremely small. Aij is nice coefficient, period 1, and uniformly elliptic. And microscopically, we assume that the coefficient in terms of the Y variable is Lipschitz. But after you divide through by this epsilon, of course, become highly oscillating. And therefore, Lipschitz become qualitative and quantitatively become very bad. Okay, the Lipschitz now blows up. So this is a standard sort of setup for period homogenization for this class of a uniform elliptic operator. And from general theory of homogenization, we can always assume that a family of operator or sequence epsilon go to 0, homogenized to a constant coefficient elliptic operator. So after suitable changing variable, you may just assume that it's a Laplacian. Okay, by the suitable changing coordinate. Okay, so operator average O become Laplacian. And we are interested in 0 set. So that is where the solution U equals 0, U epsilon is supposed to be non-zero, not identically 0 solution. And a moment ago, asked critical point set is a CU. And sometimes different people refer to as a singular set. That is the set is not really singular. Is the set where U and the gradient U both vanishes. Okay, so now we looked at this problem 5 years ago at least. So the first theorem we proved, published in 2018, is there's a Hausdorff measure estimate on the nodal set. Okay, so it's dependent on dimension, ellipticity, and the Lipschitz coefficient, right? Lipschitz coefficient, but not in terms of epsilon. It's uniform in epsilon, and the number in 0. Okay, N0 sort of measure the quantitative sort of unique continuation in some sense. And that is true for all non-zero solution inside for B2. Okay, so this theorem to be true if ABC above, assumption on the basic coefficient, and also the following doubling condition at the scale 1. Okay, so you basically require the, just one integral, right? Integral on board B2 is bounded by integral on board B1. And so at the scale 1 to 2, very behavior like harmonic polynomial in some sense of a degree n0, because you take a square. So this is really 2 to the power 2n0, right? So yeah, so so you have this, and we need this little delta here. Of course, for this inequality, this assumption, of course, you can assume delta to be 0, just take n0 to be large. But somehow we want this delta 0 to be here. In the paper, we may take just delta 0 for this problem to be 1/2. And for the critical point, delta 0 will be very small number, positive number. Okay, so let's just think very naively, right? Because you know, the technical point is not so interesting to explain, maybe just something. Naively, you want to estimate a hypersurface zero set of a function, right? Now, so usually you require this function to be like a C1, and you hope on the zero set gradient non-zero, then you have the implicit function theorem. So you have find like a nodal set in this case will be like a C1 hypersurface. Then you have a hope to say estimate the measure, right? Of course, you don't have to be everywhere to say gradient to be non-zero, but most places have to. You not allow gradient to be 0 on large set anyway, right? So, okay. So the two things. First of all, you don't have a C1, of course, in homogenization. This is a well-known fact. But you have something very close. That is a uniform Lipschitz estimate for such things, which is, you know, now is like proved in even in more general context. But for periodic homogenization, that is assumed proved around 1985, and probably maybe around 87 or 6, I don't remember. That paper I wrote was Marco Aficionado. So it's a classical fact that you have a uniform Lipschitz norm boundary. So Lipschitz is not C1, but it's close enough to talk about rectifiability, you know, generic level set and so on. So you can at least start with. So that is good. But however, you have to avoid the solution, say, vanish infinite order or vanish on open set, right? So this qualitative assumption, the coefficient to be Lipschitz, even though Lipschitz norm may be huge, at least avoid the solution to be 0 on open set. But then you lose all the control. So in the nodal set, for Lipschitz continuous coefficient, or say for harmonic function, one needed to control this doubling constant all the way to the both sides R, any R, positive, not just say B2 and B1. It's based on so-called the bound on the ongoing frequency function. And the frequency function shown to be monotone function when you have a coefficient uniformly Lipschitz. But if you have just a Holder continuity with any Holder less than 1, then you can build a solution basically vanish on any open set. So long as that connected component always extend all the way to the boundary. And it's very easy, for example, in this kind of period homogenization, you can build, say, if I just want take any open set in Rn-1 omega, and then I just say cylindrical picture, so just multiple by R. So that extend up to boundary anyway, and you intersect with ball B1. Then you can have a solution to the problem without even epsilon, uniformly Holder continuous. In fact, it's Lipschitz inside, but on various bound. So but the support exactly will be this omega open set inside Rn-1 close a line. Okay, so there's no structure, no hope to prove anything. So, okay, let's agree we have to assume Lipschitz. But because the proof of a doubling condition, if you want to go all the way to arbitrary R, you require uniform Lipschitz, and here you don't have it. You look at it quantity, you want to prove frequency to be monotone, it's basically hopeless, right? Because it's involved whatever way involve derivatives of a coefficient. Whenever you take one derivative, you introduce factor 1 over epsilon. Now, prove boundedness of frequency is one way to get a sort of uniform doubling. That is one way, but there's other ways, for example, like a classical Kalman estimate. But it's even worse because Kalman also requires at least uniformly Lipschitz. That is the best possible. It's not surprising, right? Because unique continuation is not true beyond that. Okay, so we first started with this assumption, and we want to get the other way, so the quantitative unique continuation. So there's a lemma, a little lemma. Sort of the interest in proving this measure estimate is this lemma. So you give me a delta 0, which is not integer. It's non-zero, between 0 and 1 strictly. You take 1/2, for example. When you have assumption at R equals 1, right? Assumption, we assume that this inequality at R equals 1. Then you can get for every R all the way to the size which is compatible with epsilon. And epsilon 0 is a positive constant. It's a positive constant. There exists epsilon 0 positive, right? So that positive, so that you have a doubling estimate. So basically, even though you don't have a monotonicity, somehow at least the upper bound of the doubling constant, you can go all the way without increase anything. You know, you say, well, U epsilon is close to harmonic function. So maybe each time you give a little bit factor, then you will have such inequality, very kind of cheap. But whenever you introduce even very tiny factor, slightly larger than 1, then you are in deep trouble, because after many, many iterations from scale 1 to epsilon, you will have accumulation like log 1 over epsilon. Okay, this is one of the standard problem, is sort of turning issue. And here, so long as you avoid integer, you can go all the way. In other words, if it is true for R equals 1, then it is true for R equals 1/2. Nothing changing. This constant are not changing so long as epsilon 0 is small. Okay. That has a lot to do with the fact, the following sort of intuitive fact, which for people work on these related problems, people often know, even though won't state it explicitly, is the following. Say like for harmonic function, if defined on large enough annular, this frequency you will see is a monotone. So monotone continuous function, and you can take all the value in between, right? Started at the R equals 1, you have some large number n, and then you decay, maybe, you know, when R go to 0, become vanishing order. So anything in between. But what happened is most time, for most R, so you have to define properly what you mean by that. The ni is close to integer. Okay, it's sort of like you most times stay an integer, and then you have a fast transition from the integer k to go down to k minus 1. And then you stay for a while, and then go to k minus 5, maybe. You can have a jump. Okay, but at most time you stay in the integer. And if you choose a delta 0 in between, somehow you avoid all these issues. All right, so this is a funny argument, but it's based on this intuitive factor. Okay, now for R small then afterwards, which is a compatible. If epsilon 0 is small, but whenever you fix it, it's a large constant. So this number here is compatible with epsilon. So when you reach this level R, you can scale once by epsilon, then you got the Lipschitz coefficient. And therefore, when you go to small r, the doubling will be automatic. So we solve this issue, and then you got this nodal set estimate. All right. So the philosophy here you see, right? So you use certain weak sort of closeness of this U epsilon to harmonic function. So you go down all the way and you prove this nice kind of replacement. You just got a certain uniform doubling, and then you somehow able to get it. So the main is again very similar. So now it's a solution defined on board V2, and solution is not constant, right? Solution is not constant, of course. Otherwise, it doesn't make sense. Critical point, which including in particular those zero and gradient zero set, singular set in particular, is bounded by a number dependent again on this n0, the doubling at scale 1, and ellipticity and this local Lipschitz microscope. And you also have the uniform Minkowski content estimate, right? The R-tube neighborhood of that is bounded. Okay, but beside all of the ABC condition, the structural condition on L epsilon, here you needed to make one aside of a positive found from below. Okay, and that is X is on the, because of period 1, so it's the condition is on Tn. So what is chi? Chi is called the first order collector in homogenization. And so it's explicitly a solution on the Tor. You know, on the Tor, you have a unique solution, chi up to constant, and you can take an average value to be 0. On the Tor, you have this equation has a unique solution, right? Because it's a certified Fredholm condition. So this determinant non-zero condition automatically verifies in n equals 2. In 2D, it's a lot of factors point to the same thing, okay? This x plus chi x, like in 2D, it's like a Riemann mapping, global. So it's related to quasi-holomorphic, quasi-regular function, quasi-conformal mapping. And so you can show actually it's always non-singular. But in high dimension, for example, if you know divergence is small enough, right, in certain norm, then this condition also satisfies automatically. But in general, it's not clear that determinant will might be somewhere 0. Right. This is related to some well-known factor proved by Hans Levy in 1930s, publishing Arnold several papers, 2 papers there. In 2D, he proved harmonic homomorphism had to have, has to be diffeomorphism locally. And you have a Jacobian low bound. That is how he used that to prove non-Dampierre a priori, estimate in classical 2-dimension case. And this factor is true for harmonic map, plane as R3 to R3, but given by gradient of harmonic function, he proved the same factor. But it's not true in 4D or higher. Okay, so 3D, you may still have a little bit of chance to prove, but we don't know actually. In 3D may fail in general because it's not for harmonic gradient anyway. So now with this collector, so let's see if we can go anything further. So this can be naturally explained why we need a collector condition, because say this is a homogenized solution, so that U0 will be harmonic. So this will be sort of, you can choose optimal approximation or whatever approximation. It's a harmonic function, and you link a 0 set and 0 set of a harmonic functions through this thing. That is a necessity in order to get O epsilon sort of approximation. So if this happens to be singular, a 0 set could be hypersurface in some cases, then of course you won't get anything, even you have full knowledge of harmonic function, but in homogenization, you completely lost information. So we avoid that. Of course, the best sort of convergence rates when you approximate U epsilon by harmonic function is O epsilon, cannot be anything better, okay? And you choose proper boundary condition. For example, you have the same boundary condition in smooth case, and then you will get O epsilon, but nothing better. So it looks like that you are in good situation, but it does not work like that. Even you have a quantitative unique continuation. Why it doesn't work? You have to looking back how we do for harmonic function. And even for harmonic function or for smooth PDE, to estimate the critical point set, it's much more complex than just estimate the nodal set. For whatever reason, I not fully appreciate a lot of reasons. But it's understandable because it's called dimension 2. It's just much harder to control. So let's look at it going back to harmonic function. Okay, so if you find a way to do in some very nice way for harmonic function, and that allows certain perturbation, probably, and so that will work for homogenization. That is your hope. But if that method works, then it had to work for smooth coefficient, say Lipschitz coefficient. That method you have. Because for Lipschitz coefficient, so you have all the doubling thing, all the same, right? And then approximation, now instead of L epsilon, you have a weak convergence, you have a strong convergence of a solution, maybe even in C1 alpha, C2 alpha norm, and so on. So if you can do for homogenization, that must be possible to do for any Lipschitz coefficient, or at least, you know, for smooth coefficient. So when you try to do, you know, you have to somehow face in certain obstacle, because for Lipschitz coefficient, very related to a theorem of Nava and Volta, which is not easy paper. You know, a general theory afterwards they develop is a rectifiable Latham-Berg. But this one, you don't have to use, but the proof involve quite nasty covering and so on. All right, so let's looking back at zero set and critical point set for harmonic function. So for harmonic function, right, normalize, it's non-zero, so normalize boundary integral to be 1. And you look at this quantity. I just defined for n1, you can define for nr, right, or the radius r. And that is nr will be monotone function in r, so bounded by n1. So let's assume that. And then you look at the zero set, critical point set, and the singular set in the same way. Now for zero set of such harmonic function, always analytic coefficient, then you have very explicit bound. It's just a linear in this frequency. So the hypersurface measure inside the ball B1/2 is dimensional constant times this arm-grain frequency value at the ball B1. Okay, so this is proved in my paper explicitly, but in some sense that you can also derive from Donnelly-Fifferman's proof. Okay. All right. So, and then for harmonic function, you can easily believe that kind of a conjecture should be true, right? So for co-dimension 1, you have n squared. For co-dimension 2, n linear, and co-dimension 2, you should have n squared. Why this is so? Because this is true for degree n polynomial. Okay, if you have a degree n polynomial, and if a zero set, say, is called dimension 2, then you got this estimate. This is a well-known theorem of Mellner and Tom. So in classical algebra geometry, and some version of Olenek and Petrovarsky. But this explicit bound is in Mellner's paper for polynomial. So because you believe frequency bounded by n1, the function should behave like a polynomial of a degree n1 locally, and therefore you expect it. But this is not proved even with almost sort of trivial factor. So this just tell you something is going on for co-dimension. So now let's recall one of the typical structure for for a singular set, say for harmonic function or smooth PDE. So that is in the paper of Hein, Hart, and myself. We started with this structure. So you look at a critical point set for a harmonic function, yeah, with a doubling index, this doubling constant is say all bounded by n0 plus delta 0. Then this singular set or critical point set, right? This set can be decomposed into following way. So there is like a highest sort of one with vanishing order like a highest, and then you have lower ones, but they are still stratified out. And then you have a junk in between, right? A lot of cuspers, because even algebra by the zero-set of polynomial, you expect a lot of cusp. So these are covered by with the HN-2 measure as small as you want by bunch of balls. Okay, so this is a general structure. So what is the Sn0 looks like? And similarly for all the Sk, k between 2 and n0 minus 1. Well, k equals 1 is just nothing there, right? Vanishing order is 1, so there's no critical point. So each Sn turns out, yeah, each Sn is covered by abundant number of balls. Number has estimate as well, say covered by half of these balls centered at the various point. But in each of these balls, one has following picture. So it's a very intuitive way of explaining that the function is close to a harmonic polynomial of degree n0 because you are looking at the set Sn0. So it's a harmonic polynomial of two variables of degree n0 plus higher order, okay? And the angling frequency is bounded by n0 plus delta 0, and delta 0 is very close to 0, but it's positive. And if you use a Fourier sort of spherical harmonics expansion, and then you read out the condition. Okay, so what this tells you? Well, because this harmonic polynomial, you can write out explicitly because in two variable and homogeneous, so you can think it's like r to the power n0 cosine n theta, right, with proper rotation of the theta, right, theta angle function. And then you know the gradient to be 0 is basically on this near here, right, near here. So if you do so, you basically say all the singular set is very, very close to this flat plane, which is Rn-2 cross 0, right? This is the R2 in this direction. So it's all close to horizontal plane. But it does not say that is graph over horizontal plane, horizontal Rn-2, nor is anything. It's because it's just algebraic varieties, for example, or analytic variety in general, even using analyticity, right? But then you want to estimate basically what's the measure. And you basically you're looking at, you intersect with vertical two-dimensional disk and look at the intersection number. And because the boundary behavior like that, so you have well control on the intersection number. And that number is given by sort of Roche taper theorem, but for C2, this is called the Botos theorem. But it tells you basically when you intersect with two-dimensional vertical, say two-dimensional disk, the intersection number, the singular set at the most is n0 minus 1 square. It's a square come out, okay? Because you have basically say you have a polynomial of a degree n, okay? You take a gradient, you have two functions, now polynomial degree of n0 minus 1, okay? But you have two independent functions. You can draw just a horizontal in two disk, horizontal n0 minus 1 lines and the vertical n0 minus 1 lines. The intersection genetically will be n0 minus 1 square. There's no other better estimate. That is optimal. So with this vertical intersection, whatever it is, maybe not graph or anything, but the number almost everywhere, the number is n0 minus 1 square. And then use just Federal's general co-area formula tells you the measure is bound by locally on here is bound by n0 minus 1 square times a dimensional constant. Okay, so you are confused, say, well, that is what you want to prove in the conjecture, right? n0 square and times constant. Well, all the tricky point is that involves some small ball uncovering, and you don't know how many balls you needed to cover this. How small ball has to be, right? So all this kind of dirty hiding in this structure theorem, but when you work out, you don't get the right power you want. So this is so what happened in smooth PD? Smooth PD means suitably smooth, sufficiently smooth, and that is handled in this paper. That is, I believe, it's 99, 98, right in the 97, so probably 99 CPAN paper. You can take a look. Better for suitably smooth, but smoothness unfortunately depends on vanishing order. Okay, so basically you require Cn0 square smoothness of the coefficient, and then you sort of use basically all the Weierstrass propagation theorem, but involves the finite smoothness. So it's non-trivial, but it follows from the classical algebraic geometry way. All right, so that is the story. So now let's do something differently. So we look at a singular set, right? We look at a singular set. And we make a decomposition into AK. So what is AK? AK are those radius RA. At each point A belong to AK on the, say, singular set or critical point set. You define a radius. This radius in this range, theta 0 is again fixed constant. May be different from the theta 0 in the structural theorem. Here, the theta 0 is explicit. You can take the theta 0 to be, say, 1/32 will work. If not, 1/64 definitely will work. Okay, so a few times that will work. And then what is that? That is, you have a monotone property. So from R equals 1, your monotone decreasing. But so long as your R stay larger than this number, RA, the frequency may drop because starting at 1 is like N0, capital N0 plus delta 0. So you just drop a very tiny delta 2 delta 0 at the most. Okay, and therefore, for smaller radius, the frequency will be small. Okay. It's okay. So better define all the radius. And the now critical point set is decomposed in all these AK, and AK for each point in AK, you have a definite so-called well-defined radius. So you can come from all the way 1 all the way to RA, not much changing. The frequency only drop by 2 delta 0. Now in this range, you look at it, for each R in this range, R is larger than RA, less than 1. In all this range, you look at the L2 projection to the mode, the Fourier mode at each radius, Fourier mode K not equals N0, it is actually controlled by total norm multiplied by this delta 0. Okay, this is optimal, by the way. You frequency drop by delta 0, then you norm only occupy delta 0 kind of constant time delta 0. And the whole norm, again, is also bounded by just the norm on the case mode, N0 mode. So this is elementary lemma, a little calculation, the acute calculation. And this is very useful. Okay, so we have a picture from 1 all the way, you go to R0, and basically control in each radius controlled by nth component. Okay, nth component behavior like this Pn0. You see that does not change it by separation variable. So So you have that. Now the next one, when you reach RA, you want to go down at least some fixed, say, factor. So say I go to RA over 10. Then this frequency will drop. But the drop before it's dropped by delta 0, now is delta 0 to the power beta 0. You may find this slightly mysterious. Where does this power come from? So that has something to do with following function. Okay, so let me see. RUR minus N0 times U. Okay, so you look at this function. This function is a harmonic function. If you have a harmonic, you have a harmonic function. Okay, so this is good. It's a harmonic function. And then the hypothesis that the frequency, basically you drop from 1 to all the way here. So on this big annular region, the frequency drop only by delta 0 just means this H function, L2 norm on this whole annuli is like a delta 0. Because the function is close to homogeneous degree N0 harmonic polynomial. And if it is N0 degree harmonic polynomial, this quantity will be identically 0. So it's a small perturbation, it's delta 0. Okay, so we basically have a harmonic function. This is RA and O side. And on all the way on this annuli, the harmonic function is bounded by delta 0. Now, when you apply the three-circle theorem, this is a bounded function, three-circle theorem, even you after normalization by R0 to the power N0, R to the power N0, apply to this, and then you find this is true. So this is really a statement about three-circle theorem, three-sphere theorem. Like a Hausdorff three-sphere theorem, you have that. So basically you say you have a Cauchy data for harmonic function bounded by epsilon. Then, on this ball B1, when you go to ball B2 and function defined on ball B3 to be bounded, say, then on ball B2, at most is like epsilon to the power alpha or beta that we use. Okay, so this is second one. So in other words, the character are not changing, right? Because the delta 0 is so small, you choose. That is no problem. Now, the another one, if you hit the number, okay, if you hit the number for 1R, that it start to say like RA. When you hit RA, right, the frequency is dropped all the way to N0 minus delta 0. Remember the RA definition, right? It's when you hit this number, its frequency just right below N0 minus delta 0. Then if you're willing to give up this delta 0, the optimal one might be some constant times square root of the delta 0, but it's immaterial for our purpose. Say, let's shrink all the way to delta 0R. Then the frequency actually is a one integer below at least. Okay, so you say if it's actually you lay below N0, you're not going to last very long. You have to drop to N0 minus 1, more or less near there. That is what I said. The frequency can never stay very long time away from integer. So long as you stay below this integer and monotone decreasing, and then will be stay below, close to the next integer, below that. Okay, so these are basic fact about the harmonic function. Is this okay? I'm go kind of, I'm for sure I'm run out of time, but I want to give you some sort of idea. Okay, so with these three, now the next one is more important. It's a more geometric observation. But AK, remember, are those RA, IK, this radius is between theta k and theta k plus 1. All right, so this drop from N0 plus delta all the way to N0 minus delta 0. That are these AKs. And each AKs cover by this R corresponding bunch of balls with half of the radius, right? So that, divided by 5 will be mutually disjoint. So this is like a Vitali cover. Okay, you just choose a Vitali cover, covered by the half, and 1/5 of the half, so 1/10 of that will be mutually disjoint. Okay. Now the geometry lemma, so this covering you can always do. So what is this geometry lemma? Geometry lemma basically say the centers are in this covering. You will say when you use 2 index, I is like from 1 to infinity. How many balls? I don't know. It's finite, but I cannot give a number, right? But the k means for a k, so k stage, right? K, for example, equals 1 is the first stage. And these centers, for any given k, the centers always lay in a Lipschitz graph over same horizontal n-2 dimensional plane. With Lipschitz norm is exactly this delta 0 to the beta before, slightly small maybe, but it's okay. And in particular, the projection of these covering are disjoint in the downstairs here, in the RD1 n-1. So that way you can control number of balls, because these balls are like theta 0 to the power k, between theta 0 to the power k and theta 0 to the power k plus 1. And so the number of balls needed actually cover, you may come up with this number, maybe multiple by another factor, but fixed, right? Because k and k plus 1. And the function, harmonic function approximate in whole range, never changes in all these problems. You have a scale 1, B1 here, and this is say one of the ball with radius RA, you have this picture. But you look at the gradient equals 0 for this harmonic function, it's always near here. So you find a sort of cone type region, very tiny opening. The opening is delta to the 0. This opening is delta 0 to the power beta opening. And so that the shaded region, the black here, shaded region, is the only possibility inside this. I shouldn't say, yeah. So if we just one ball, this and then the shaded, all the critical point has to be inside here. Whenever you have such a ball, all the critical point might not be on the center, right? Somewhere else. I draw a dramatic. Okay, so critical points there, I have no control inside of these balls at the k state, right? But otherwise, horizontal Lipschitz. And so suppose, this is some, not necessarily B1, but suppose you have far away another ball. So all these ball centers on Lipschitz graph. Okay, so if I want to draw a picture in physical dimension of this covering, I don't know how many balls are actually in A1. Say, for example, A1. So I have a bunch of balls, and then maybe disconnected. I really not draw very well. But all these centers are laid on Lipschitz graph with very tiny Lipschitz norm above this horizontal one, horizontal Rn-2 plane. This is extremely sort of useful control. Okay, say if just at one stage, if all these balls used to cover A1, okay, and then so I have no idea where the singularity are, but then it become like this size of this ball, say, is theta 0 and theta 0 square, right? In between these, and if I take a theta 0 neighborhood of this presumable Lipschitz graph, you use extension with small Lipschitz norm still, and then it is stay near in nearby epsilon theta 0 neighborhood of this graph. So you can efficiently cover. Because the Lipschitz norm is so small, and these balls, say 1/10 of these size balls are disjoint. In fact, 1/5 of that is disjoint or something. And then you look at its projection, right? You project down into this Rn-2. In fact, inside B1 n-2 0, you will see a if you just look at middle 1/10 or middle 1/4, these balls are, right? These balls, okay. But these balls are disjoint. If I take 1/10 of these balls or 1/4 of these balls, cannot above these balls, 1/2 of these ball may have overlap, but since 1/10 is completely disjoint, or 1/5 is already disjoint. So downstairs, when you project it, because it's the graph essentially is a horizontal. So your Lipschitz norm is so tiny. So these balls, 1/10 of these balls, and you just project down, you just find a bunch of the balls of 1/10 of the size, right? Theta 0/10, say. They are completely disjoint. So this is A1. All right. So we have A1. Now, and you use this size of ball to cover, and first you give a covering. Now you do next stage for A2. So for every AK, basically contained in centers, right? Centers contained in gamma K with Lipschitz norm. No, or this thing like delta 0 to the power beta 0, so beta 1. Okay, so now you basically when you go down scale, so you have infinite many Lipschitz graphs. How these graphs sort of, relation between these graphs? You cannot be, because each one, whatever you do next time, they still have to lay in the theta 0 neighborhood of first graph, and then you do, and so on. So there comes a little bit tricky sort of argument. You basically, do a lot of the slightly small geometrical argument in some sense. So you have to classify those. For example, this is one ball, A theta 0 belong to A1, say, right? It used to cover the A1. All right. Now, maybe this is a point in critical point belong to A1. So its center A belong to A1. I should say that, right? Okay. Now, you may have a situation beside A1, there may be no other critical point, but there may be a lot of A1s inside of this ball. They are not laid on not necessarily same Lipschitz graph, but because when they are disjoint from each other, right? Then you know this ball and this ball cannot be far away because this picture here. Because this picture here. You see, if these balls are far away, you can guarantee they are on Lipschitz graph. But if these balls are almost same ball, well, how do I know? I may have another ball here, and you just lost control, in other words. So you really have no control inside here. But if you happen to have, say, some point here, right? Some point here belong to some AK. Then you will have tiny little ball here. Then everything has to be on very outside of this very tiny ball in very small kind of strip. Again, the same picture as before, because the frequency does not drop. So even you have all the A1 point here, it has to be laid on small thing. So there are two possibilities. Either you will see some other layers of critical points that appear in the K step of a gamma K. Lipschitz graph will go through this given ball for A1, for example. Or otherwise, you just don't see any going through there. So if there's no other point, say this is in A1, and this is a half of ball, right? This is used to cover. And if there's no other critical point, then what you do, well, then you just cover half of this ball, right? Half of this, because it's inside here, delta 0 size, say this is theta 0, and multiple by delta 0, all the critical point here. You just pick up any point and you cover by just by delta 0 times theta 0 balls. Okay, how many? Well, whenever you go from 1 to delta 0 ball, if the center say in A1, the frequency drop from N0 plus delta 0, and here will be N0 -1 plus delta 0. Okay, so when you use radius instead of say r and you go all the way delta 0 times r, then on this ball, the inside the ball, the frequency is already dropped by a whole integer. So what I have now is either you see some critical point like here, then you have much better control. You have all these A1 point, nowhere to go, had to be in same strip. You can go to next scale. Or otherwise, well, they have a freedom, but how many balls you need to cover? Well, delta 0 balls, not many, right? It's a constant depending on delta 0. Basically, it's delta 0 to the power -2 because each size is delta 0 times r. So inside r ball, you use delta 0 r ball. So this, but then these points will have a frequency doubling index bounded by n0 - 1. So that tells you you can do induction on n0. So you prove from very beginning the structural theorem that you have this or that. So if at some point that the ball cover, you don't see any other lower level ones, you just basically these critical points are already in here. So you do just induction in this case. But if you have, you just use gamma k. So basically you will say, if you pick up a ball, cover A1, you don't see any other critical point. You just leave it alone. You just do next stage, A2 and gamma 2, Lipschitz graph and AK. You just keep going. Whenever these balls do not contain all the, next generations, then you can simply throw away eventually. And so this gamma k part will not, you don't need to count a gamma k graph inside of these balls because you throw away in the next state. But these balls, when you look at the projection, the next stage balls say outside, and some of them inside, and some of them inside and outside, and some of them just there's nothing, say use second stage. But these balls, when you use second stage, and some of the balls could be go inside. So these small balls, and then they are very large balls. These large balls and small balls, the projection will be always destroyed. So what this means, even though above you have complicated picture, but you shrink a radius by 1/10, right? Just multiply by 1/10. Then you look at the projection, well, they're disjoint. Well, if they're disjoint, you can add up all the measure and counting number of balls and compute exactly the n-2 dimensional measure. And then therefore you have Hausdorff measure control. But this process of proving from large ball to small balls also tell you how to control Minkowski content. All right, so this is a proof for harmonic function. I'm sorry to take it much too long, but this is a very different proof from all the previous one. Okay, so I wave hand a little bit, with this kind of tiny little things of the technical point. You do careful in this argument and the cover. After you finish that, so now you become layers of balls when you go down. What is important is you trace the sum of the point. You can go from one ball all the way actually to theta 0 to the power k. Theta 0 to the power k. K is very, very large. And some of the points, critical point, you just stop there, like I say theta 0. Afterwards, you don't see any, right? So you have layers of balls. And then for each layer, when you go in from 1 to theta 0, you use a harmonic approximation. So you have to adjust the harmonic approximation in the homogenization. So for harmonic function, I'm done. But how to prove the same thing is true for homogenization? Then you have to say from one ball to theta 0 ball, I go just by harmonic one. I use first harmonic approximation. And then I go from theta 0 ball to theta 0 square ball, right? I use next one, least scale, and use different one. I have to check each time what's the difference. And so I have to trace what is the homogenization error. And the good thing is the homogenization error is always epsilon. Say you have a k step, theta 0 to the power k. And you always have this to certain power at least. In fact, the optimal power is 1. So you just take 1/2 power and you add up. It's still, right? K from all the way to epsilon size, the epsilon 0 to epsilon -1 to epsilon 0. But it's still bounded by epsilon to a certain power. So it's very tiny. This becomes a homogenization error you add up. And when you trace what is sort of the frequency drop, okay? So harmonic function frequency always drop, but when you have a jump or like at each boundary of a theta 0 ball, there is a homogenization error, okay? So you have monotone decreasing of a frequency, and you stop at RA or RA over 10 when the frequency drop, say, exceeded from N0 plus delta 0 all the way to N0 minus delta 0. Then you stop, because there suddenly you see the middle singular point or critical point is already belong to next N0 is N0 minus 1. So you use this kind of a double induction to get right cover. So the whole argument was published and is posted in it's a tracing of this calculate this geometry idea carefully and trace out. And we use a slightly different covering in that paper. Okay, so basically I finished. I thank you very much. The proof. I'm very glad actually. This is 1 hour. Sorry, I should have stopped a little bit earlier, but okay.
Thank you. Thank you for this interesting talk. I really didn't know much about this problem or the literature.
Oh, you just need to find a better proof for harmonic function. You see, before use analyticity, right? And then use like a Roche taper serum for like a 2-dimensional complex disk. Or otherwise use the Weierstrass propagation serum for finite smoothness, subunit high smoothness, depending on vanishing order. And you get the number of intersection and directly estimate. And here we just go zoom in all the scales. And you will say, why I need to change in this harmonic approximation? Well, no matter what you do, you use the harmonic approximation at the radius 1. And the error, optimal error is O epsilon, right? Now suppose I have a function. The vanishing order at the origin, say, is N0. So what's the function value will be how big a radius I can take. Has to be epsilon to the power 1 over N0. So you can go down the harmonic approximation. The best you can do is from epsilon to the power 0 to all the way to epsilon to the power 1 over N0. 1 over N0, right? It's much less than 1. So in order to reach all the way to epsilon, you have to iterate many, many times. And this number of times you introduce error. If you not trace carefully, you introduce error of log 1 of the epsilon turning. You see in this picture I have here, at one scale, you have this picture. You can always reach this picture. But when you go to next scale, this picture a little bit turned. It's in all the geometrical analysis problem is you use best harmonic approximation. You have one tangent plane, the next tangent plane. The plane rotates. Each time very little. But how many steps? You basically take log 1 over epsilon steps. So each time is very tiny. I don't use eta 0, say log 1 over epsilon. But this kills you. So I'm going to rule out all the rectifiability and all the troubles. Yeah. And I cannot use the frequency. Yeah. Monotone. Okay.
Can I ask you a question, Fanghua?
Yes, yes, please. Hey, Leia.
Hi.
Okay, yeah.
I enjoyed the talk. I like N1. Actually, I had read that paper from Avellaneda and you many years ago, but I haven't followed so closely.
Yeah.
So can you go back to that HN minus 2 estimate, the crucial one that you said? The conjecture. Yeah.
Yeah, this is still open.
Yeah. So
Okay,
how
so-
did they derive this for harmonic polynomials? Why were these people interested? Was there, what was that?
Oh, this is related to the topology control. For example, if we have a polynomial degree n, and you look at the level set of this, say, algebraic variety, what is the upper bound for Betti number, for example?
I see. Okay,
Yeah.
more things that I don't know about.
Oh,
So the
yeah.
so is there
John Milner's paper is to estimate the Betti number.
I
The
see.
Betti number eventually is just intersection of in n dimension intersection of zeros of n polynomials of a degree less than capital N.
So not necessarily harmonic,
Number of zeros, yeah, generic just counting number of zeros.
but not necessarily harmonic.
Yeah, well, in some way, if you have a polynomial, you can look at a projective space and then become a degree in projective space. Polynomial. Yeah.
I'm curious
So
though, under
see
any
those
condition.
ways.
So there's also maybe not including this N1, but no, stay where you were. Stay where you were. So there was also like a lower bound recently that was a big deal.
Yeah. You not expect any lower bound.
Okay, I was curious.
Point. Well, you can have no critical point. So, and also
no, but I mean on higher, maybe on higher eigenfunctions or whatever.
Yeah. Part of the things, it's tricky in sense that analytic varieties like a nodal domain, right? You can have these like, divided in the board V1 into various sectors where you positive, negative, like in 2D, right? But in 3D or higher, and most time the nodal domains of sort of, almost all polynomial, harmonic polynomial, the nodal domain is connected, just two components. And the level set could be smooth, but the topology is huge still, right? The higher topology is huge. So it's a lot of tricky points. So that kind of estimate, in other words, if you stay in analytic varieties, just real, it's not stable. It's not stable. You just give little perturbation, you may not see any critical point. Yeah. But you need just upper bound. So upper bound is more relaxed. Now, what you mentioned is the above this one for general PDE, this one. So Sasha Luganov proved that for general smooth PD, say Lipschitz coefficient, there is some number, let me just call the gamma, larger than 1. You have upper bound, but you always have this lower bound also. The lower bound turns out to be true.
Yeah.
And that is his Nadelashville concept.
Yeah, I know a little bit about that. That's why I was curious.
Yeah. It's just this. I don't think there's a frequency involved. Yeah, there's a lower bound. 0 set of any harmonic function inside unit ball. And you will have this low bound, Nadelashville. But when you use covering, you will get a certain polynomial low bound and polynomial upper bound. That is his 2 Arnold's paper. Yeah, it's impressive.
Well, thanks for the talk.
Yeah, okay, because in one needed to leave early, so I will continue hosting any further questions. So any other question for Professor Lin? Okay, so that maybe I ask probably the last one. Okay, so is there any relation between the set of critical points of U epsilon and the set of critical points for solutions to the homogenized equation?
Oh yeah, yeah. You see this connection here, and that is why our assumption comes.
Okay.
You see, if this is invertible, so
oh,
you see.
Okay, I see. Yeah.
Right, but it's up to this error. So
okay.
You see the tricky point here.
Right,
So,
right.
Yeah.
Okay, I see.
And that is why you need an assumption. This is non-singular.
Right.
Even though you can guarantee this assumption by assuming divergence of A is small. So, but you need this. Otherwise, this zero set or determinant equal zero set could be quite big.
I see.
At least we don't know.
Okay.
In higher dimension. In 2D, actually never zero. That is because 2D is just always spatial. It's related to quasi-conformal mapping. So if for say period metric on R2, so conformal taper will be R2, right? Because it's uniformly elliptic. So R2. And so there's a Riemann mapping. And this one is exactly Riemann mapping, turns out.
I see.
And the minimum gross harmonic function consists of x1 plus chi1 and x2 plus chi2. These are two independent. So the minimum gross harmonic function. This harmonic respect to this Aij, of course. Yeah, so Riemann mapping is always given by a minimum gross harmonic function. This is the one of the exercises I did at like a second year graduate time or something. Yeah. Published a silly paper with Wang Ni in communication PDE. So that it probably was my earliest paper.
Okay, great. Any other question for Professor Lin? Okay, if not, let's thanks the speaker again.
Well, thank you. Okay.
Thank you.